Now that we have some concepts of the waveforms and the samples down, let's head back into the code. The next operation we're going to do in wave compute is y equals 0.8f times BasicSaw address of op1. Our argument is address of op1. We will store amp, frequency, phase, and out in the op1 oscillator type struct. Our sample value will be stored in y. The value of the sample we obtain from BasicSaw will be multiplied by 0.8f. This multiplier is used like a volume setting. Effectively, we will reduce the sample's amplitude directly here by 20%. So if the sample equals 1, it will become 0.8. If the sample is 0.7, it will become 0.56. This will become useful later on when we use more than one oscillator at a time. Many times we will be referring to the values of pi and 2 pi. Both values are defined in constants h as 2 pi, 6.283185307f, and pi as 3.14159.265f. These values are defined very long with 8 to 9 decimals each. To simplify the following exercises, we will use the values of 3.14 and 6.28 instead. Additionally, there are many times we will see op in front of a variable. Instead of continually saying op, it will be dropped off and only the variable names like phase, amp, frequency, out will be used. Let's look at BasicSaw. While this may appear complex, it is actually fairly simple when we break it down into sections. In the first portion of the code, we have this. While phase is less than 0, phase equals phase plus 2 pi. While phase is greater than or equal to 2 pi, phase equals phase minus 2 pi. The parameter phase is used to track where we are in the waveform's progression, as this simple diagram will show. When phase equals 0, we are at the beginning of the waveform. When phase equals pi, we are in the middle. When phase equals 2 pi, we are at the end and ready to begin again at 0. This code is used to keep the value of phase in between 0 and 2 pi. If phase is greater than 2 pi, then we subtract 2 pi from phase, and phase will likely be reassigned near the beginning of the waveform. If phase is less than 0, then we add 2 pi to phase and are likely to end up at the end of the waveform. What this will do is wrap phase values around if they are less than 0 or greater than 2 pi. Let's look at a couple examples. If phase equals negative 0.567, then we'd use the formula phase equals phase plus 2 pi, which would be negative 0.567 plus 6.28, which is 5.713. And that brings us to the end of our waveform. Now, if phase were to equal 7, then we'd use the formula phase equals phase minus 2 pi, which would be 7 minus 6.28, which is 0.72. And that brings us back to the beginning of our waveform. Now let's look at the next operation. If phase is less than pi, out equals 0.5f times amp times phase divided by pi, else out equals 0.5 times amp times phase divided by pi minus 2. So if we are operating the if statement, we will be doing these. If we're operating the else statement, we will be doing those. The if statement is checking to see if phase is less than pi. And as long as it is, it will continue to do these instructions. But the moment that it is no longer less than pi, then it will do the else statement. When the if fails to be true, then phase must be equal to or greater than pi. This code is how the SAW waveform's phase reaches the value pi mid-waveform, then suddenly jumps from +1 down to -1. If we are near the positive peak value of the waveform, phase would be very close to the value of pi. For simplicity, I show the peak as equal to or less than pi in the diagram because there is hardly any difference between the full definition of pi used in our code, which is 3.14159,265, and just 1/100 millionth less at 3.14159,264, which would be less than pi, or 1/100 millionth more at 3.14159,266, which would be greater than pi. As you'll see in the next exercises, it's easier to follow how the code works if you treat the peak positive and negative values as pi for demonstration purposes. Looking at our formula again in the if statement, it can be easier to understand if we remove the beginning of the code and just concentrate on the last half, phase divided by pi. Let's run this formula and see what happens if we make phase equal pi. Pi divided by pi equals 1. So we get a value of +1. Now let's look at the else half of the code, 0.5f times amp times phase divided by pi minus 2. Again, let's only use the last half of this formula. And now let's run it again with the same values, 3.14 for both phase and pi. Pi divided by pi minus 2 equals -1. Now, because we have that -2 at the end of our division, instead of a +1 result, we have a -1 result. Now let's try it again, but this time we will make phase equal 2 pi, which we'll represent as 6.28. So 6.28 divided by pi, which is 2, minus 2 equals 0. This brings us back to the beginning of our waveform cycle. Now what about the first half of the if-else statements? This part, 0.5f times amp. Amp is like a volume setting. The max value will be 1, and lower values will be decimal values such as 0.8, 0.6, 0.3. It's easier to imagine the default is 1, and we reduce the amplitude by using the decimal values. Later on, when we work on the envelope generator code, we will use amp to automatically increase and decrease the amplitude with the ADSR controls. No matter what the value the rest of the formula results as, this value will reduce that value by 0.5, 50% or half. We could change it to 0.8f and then we'd only reduce it by 20%. Or we could do 0.3f and reduce it by 70%. This hard set volume reduction can be used to keep the amplitude at a level to avoid clipping, which are values past positive or -1. So to put it all together, if we make amp equal 0.8f and phase equal pi, then we would have something that looks like this. 0.5f times 0.8f times pi divided by pi would break down to 0.5f times 0.8f times 1, and furthermore, 0.5f times 0.8 equals 0.4. Our final result was 80% of the max amplitude plus 1, and we reduced that again by 50% which results in 0.4. In the next lesson, we will take a look at the third part of BasicSaw, which is the phase incrementer.